All right, here we are for Honors Physics, Projectiles Worksheet 2. All right, we're going to go ahead and work this out here. It says, first problem says, a smooth marble rolls with a speed of 12 meters per second along a horizontal table whose top is 1.5 meters above the floor. So I'm going to start with a sketch. Here is my horizontal tabletop. That is 1.5 meters up above the floor. And we've got our marble here that's going to take off from the edge of the table. And we know it's supposed to be traveling at 12 meters per second along the horizontal table. So it's going to start off like this. Now, this is not the path it's going to follow, right? This is just the initial velocity, horizontal there. It's going to start falling immediately, right? Okay, it's going to drop below this path. Okay, and it says, neglecting air resistance as usual, determine the horizontal range of the projectile when it rolls off the edge of the table. Okay, let's see. We also know it's 1.5 meters up. So I know that this height here is 1.5 meters. And we're trying to figure out how far it goes horizontally from the edge of the table there. So from here to where it hits. So it's an important thing to draw in the trajectory for the projectile, the path it's going to follow. Now it's going to make that kind of parabolic path here. So I'm going to sketch that in. That's going to follow this path. It starts off going horizontal, so my pen starts off horizontal here and kind of goes, right? And so I'm trying to find what this horizontal displacement is. I'm going to mark that delta x, my horizontal displacement. There. So I'm trying to solve this problem for my marble going from here to here. All right. So for me, I think the sketch is definitely the way to go. Drawing in the path is going to be helpful when we talk about different kinds of projectile problems. You'll see that there's a bunch of things that you're supposed to just recognize in the different problems. And so seeing the shape of that path you're following is going to help jog your memory about those little tidbits of information, of projectile trivia that you're supposed to remember. So here we go. We want to find this horizontal displacement. So what I like to do next is I find that since I'm analyzing two different motions at the same time, I'm analyzing a constant velocity in the horizontal axis with an accelerated motion in the vertical axis. I'm going to have a whole bunch of variables to keep track of, right? For all the vertical motion and the horizontal motion at the same time. So many variables to keep track of. I find it really, really, really useful to make a little chart, a little table of values. So what I recommend doing next is making this table of values for the horizontal axis and the vertical axis. Okay, it looks like this. A V naught V displacement and time. A V naught V displacement in the y-axis and time. I'm going to use a delta y for, I'm going to call y my position along a vertical axis. So delta y is my vertical displacement. Moving on to here, you say, okay, I start going through. Now it turns out actually that there are a couple of values here that we know for every projectile problem. We know that for a projectile, that's an object that's only being affected by gravity. There is no force shoving sideways then. Gravity just pulls up and down. So there's nothing pushing sideways. So there's nothing to push this to get faster or push against it to make it go slower. So that horizontal velocity is going to stay constant. And so the acceleration in the x-axis is 0. And these two velocities, my starting horizontal velocity, my ending horizontal velocity, my horizontal velocity here and here, they've got to be the same. So I just go and do like a bracket and say, hey, that's going to be, in this case, that 12 meters per second. Got ahead of myself there. The other thing I was going to say that we know for every projectile problem, besides that the horizontal acceleration is 0, so these velocities are the same, the other thing that we know is the acceleration in the vertical axis. We know that the only force acting up and down on this thing is gravitational force. And that means the acceleration is the acceleration caused by gravity when there's no other forces. And the acceleration caused by gravity, we give it a special symbol, lowercase g. Now, I am going to choose my coordinate axes here. And I'm going to choose to call to the right and up positive, and to the left and down negative. And so, because I think that's pretty standard. And so that means my acceleration in the y-axis is g downward. So it'll be a negative g, which near the surface of the Earth, we know the value is negative 9.8 meters per second squared. So I can fill that in right away for all my projectile problems. Okay, let's fill in now the values that we know for this one. We know that horizontal velocity is 12 meters per second. What else do they tell us? What's this? That's going to be my change in height. So it's going to be, here, let me, you say that's going to be, I'm going to be going down 1.5 meters. So I want to make this negative 1.5 meters. And then this horizontal displacement, that's the thing we're trying to solve for. And at this point, you say, okay, I know two variables in this axis. I know two variables in that axis. Like, well, that's not enough to solve. My motion equations usually here for accelerated motion, there's 5 variables. Each equation has 4. And to solve an equation with 4 variables, you have to know 3. I only know 2. I must know another variable here that I haven't written in yet. Okay, there must be another one of these that I know. So I can just kind of run through the checklist and check each of these now. That's another reason why I like having the chart. If you find you don't have enough information, you can go back and think about each of the variables and say, wait, do I know that one? And I do know one more variable. When you see a problem like this, where the object starts off moving horizontally, turns out there is one more variable that you automatically know. And that is that at the start, the motion is all horizontal. How fast is it going up and down at the start? The starting vertical speed is 0. It's going to immediately start to fall. But at that first instant, the vertical velocity is 0. So I'm going to put a 0 there. And that's something that you have to spot in the problem from the description. They're not going to tell you, oh, by the way, the starting vertical velocity is 0. You're like, oh, no. If it takes off horizontally, I know that tells me the vertical speed is 0. All right, that's enough information to solve now. Now we're in good shape. So what comes next is that we choose a formula to model, to represent the motion for each axis. That's the main idea of projectile problems. The key idea is that we have 2 different motions going on at the same time. Constant velocity in the x-axis, accelerated motion in the y, and we can analyze each one independently of the other. So that's what we're going to do. So for the horizontal axis, since the acceleration is 0, we're going at constant velocity. There's only one equation that works for that, and that could be velocity is displacement divided by time. I like to rearrange that. So for the horizontal axis, I like to write that displacement is velocity multiplied by time. And I'm trying to find that delta x. So that's good. It's an equation for that displacement. Do I know the velocity in the horizontal axis? Well, yeah, it's a constant 12 meters per second. So if I knew the time, which I don't yet, I could just, if I can find the time though, I could put it in here and get my displacement. So I need to find the time. Now, conveniently, it's the same amount of time to go horizontally from here to here as it is to go vertically from here to here. So I can solve for the time with the vertical information and then use that time to solve the horizontal axis. So what I'm going to do is I'm going to choose a formula for the vertical axis. And I know acceleration, v naught, delta y, and I'm going to find t, because that's going to be helpful with solving the horizontal motion. So I want the formula that doesn't have the final velocity. And if you think about it, you realize that's displacement is initial velocity times time plus 1/2 acceleration times time squared. Does not have the final velocity in it. Now, in this particular problem, we know that our initial vertical speed is 0. V naught in the y is 0. So this V naught is 0. That means this whole term is going to drop out because V naught is 0. So that makes the equation a lot simpler. My goal is to find delta x. Here I've got an equation now. Delta y is 1/2 at squared. And I know the a. I know the delta y. I can solve for that t and then put it in here and solve. But I'm going to do this with variables first. So I'm going to take this expression And I'm just going to rearrange this and say, hey, you know what t would be? Move the 2 over, multiply both sides by 2, get rid of the half, right? Divide both sides by a, and then take a square root, and that would be the time. So that is what I'm going to move and put in here where it says t. So I'm not going to put the values in yet. Let's just leave this for right now. We'll come back and put the values in a minute. Leave this as v, right? And then where it says t, I'm going to put in that root 2 delta y over a, square root. Wish I hadn't started putting that number in. All right, so this then, you know what this is? This is the answer, what I want, in terms of the variables that I already know. I know what the horizontal velocity is. It's 12. I know what the delta y is. It's negative 1.5 meters. I know what the acceleration is, negative 9.8. By the way, notice that negative 9.8 and that negative 1.5, the negatives will cancel each other out. Good thing, because that's a square root. Don't want to have to take square root of a negative. So I can see now exactly what affects my final answer, which is kind of neat. It's a good reason to do things through with the variables first, because you can see exactly how things affect the answer, which is what they're going to want us to do in this next part. All right, but for now, if I want to put the values in, I would say, okay, my horizontal displacement is going to be my velocity of 12 meters per second times the square root of 2 times my displacement, negative 1.5, over acceleration, negative 9.8, right? And that's something I can punch in my calculator. Negatives cancel, so 3 over 9.8. Take the square root of that and multiply by 12. And I get a displacement of 6.6, and it's going to round up to be 6.64 meters. Which takes us to part B, where they'd like to know what change occurs to your answer if, and I'm going to solve using variables only, that's why I didn't want to plug the numbers in yet, solve just using variables here. If the speed of the marble is doubled, what is that going to do to my delta x if I double the speed? Well, look, with this equation that I came up with here, do you see that? What's going to happen to this if I double that horizontal speed of the marble? So that equation I came up with was delta x is v times the root of 2 vertical displacement over the acceleration. Okay? That vertical acceleration, right? Horizontal acceleration is 0. It's vertical acceleration. So take a look at this horizontal velocity, vertical information. Okay. So the question is, hey, they want to know what happens to how far it goes, delta x, if I double the speed of the marble. So I'm not changing how high the table is. I'm not changing the acceleration due to gravity. I'm just going to double v. So this side of the equation equals this side of the equation, right? If I make a change here, I got to make a change here to balance it out. So I'm not changing these. I'm just going to look at my changes. I'm going to double v. What has to happen to delta x to keep the sides equal? It's got to be doubled. So my horizontal displacement will double. Okay, let's try that again now for the next part, for BII. What happens to my answer, that's the displacement, sideways displacement, if I double the height of the table this time? So again, I'm going to start with that formula I derived for this problem, that expression I derived for just this problem. Delta x is v, that's the horizontal velocity, times the root of 2 times vertical displacement over acceleration, the y-axis. You say, what I'm going to do now is I'm going to double the height of the table. So I'm going to double this delta y. So the change is I'm going to multiply this delta y under the radical by 2. Now, whatever change I do to this side of the equation, I got to do the change on this side to balance it out, right? I'm putting basically, it's as if I multiplied this side by a 2 under a radical. I multiplied this side by the square root of 2. I have to multiply this side by square root of 2 to keep the sides balanced. And so the answer is it will be square root of 2 times as far. So that displacement is root 2 times bigger. And that was a lot quicker to do if I had this equation with the variables. It's a lot quicker to just really quickly check and see what effect things have, right? Rather than having to run through the whole calculation over again with the new values in, which is a nice reason to solve through with the variables first before putting your values in, because it lets you see exactly what affects the answer and how it affects the answer. All right, so that's the first problem.